So we've talked about limits at infinity for polynomials. Now we're going to talk about how to look at limits at infinity for rational functions. Real quick before we jump into that though, one definition here says the behavior of limits of polynomials and rational functions as x approaches positive or negative infinity is called the end behavior. So a lot of problems might say, hey, find the end behavior of a function. And really all that's asking to do is saying find limit as x approaches infinity of f of x and limit as x approaches negative infinity of f of x. So hopefully that's a term that you remember from college algebra, but if not, that's what that means. It just means go find the limit at positive and negative infinity here. So here in example 4, it says use limits at infinity to determine the end behavior of each function. If there are any horizontal asymptotes, find them. So let's look at part A here. Let's say I wanted to start by looking at limit as x approaches positive infinity here of 5x plus 4 divided by x squared minus 2x plus 1. So if I wanted to evaluate this, your first thought might be, okay, well, what happens if we take that number and plug that in? So what if we were to take, say, infinity and plug that in? So if I wanted to do that, we could try it here. 5 times infinity plus 4 divided by infinity squared minus 2 times infinity plus 1. What I would have here is infinity plus 4 divided by infinity minus infinity plus 1. And we run into some problems here where, okay, what does infinity minus infinity look like? And even if I did, let's say it's infinity here, what does infinity divided by infinity look like? I don't know. All of these are indeterminate forms, which means we don't really know how it behaves. We need more information here. So this method is not going to work for us for rational functions. If we're approaching a finite value, sure, I would encourage you to do that here. But if we're approaching positive or negative infinity here, that approach is just not going to work. So we need to try something else. So what I'm going to do here is I'm going to look at the highest power of the denominator, the term with the highest power of x in the denominator. So here in this case, it's x squared. So what I'm going to do, you can think about this as multiplication or division. I prefer multiplication here. I'm going to multiply both my numerator and my denominator by 1 over that highest power of x from the denominator. So 1 over x squared here. Again, I'm getting x squared from this guy right here, that highest power of the denominator. And what I'm going to do is I'm going to take this 1 over x squared and I'm going to distribute it to each term in my numerator and each term in my denominator here. So I'm going to show you kind of the long way here, and then you can maybe take a shortcut if you're feeling comfortable. So we're still looking at limit as x approaches infinity here. My numerator, I'll have 5x over x squared plus 4 over x squared divided by, in my denominator, I'll have x squared over x squared minus 2x over x squared plus 1 over x squared. And so if I look at this, you might say, okay, well, we've got some like powers of x here and here and here. Why don't we reduce those? Let's simplify this a little bit so that it's just a little bit nicer to work with. So here I'll look at limit as x approaches infinity. I should have 5 over x plus 4 over x squared divided by 1 minus 2 over x plus 1 over x squared. And what happens here is that we basically guarantee with this method that that denominator is going to approach a finite value. The numerator, I'm not sure what it's going to do. There's no guarantee, but the denominator will always approach a finite value here. So what I'm going to do is I'm going to look at the limit of each one of these terms separately. So the limit of 5 over x. So the limit of 5 over x as x approaches infinity here. Well, I have that power of x in the denominator. My numerator is a constant, so that's got to go to 0. Same story for this guy right here. Same story for 4 over x squared. I have a constant in my numerator, a positive power of x in the denominator, so that's also going to approach 0. Divided by, all right, what's next? Now I've got 1. Well, 1 is just a constant. It doesn't depend on x, so the limit's not going to affect it at all. It's always just going to be 1. Minus, okay, well, 2 over x. Again, I have a constant divided by a power of x, so minus 0. And then finally, 1 over x squared, so plus 1 over x squared, that's going to approach 0. So I have 0 over 1. I know exactly what that is. This approaches 0. So my limit as x approaches positive infinity here is just 0. Really quickly here, I'm kind of running out of room, so why don't I erase this part up here? Because when we talk about end behavior, we generally want to know the behavior at positive infinity and negative infinity as well. So I'm going to look at limit as x approaches negative infinity as well. And what I would do here, I would just take this simplified form. We did all this work to get this form. I would actually just take that and evaluate the limit of that guy, because it really says the exact same thing. It's just, it looks a little bit different. The equation itself will have the same output for 99% of your inputs. It's just for a very, very small portion of them, but the limit should be the same here. So I'm going to look at 5 over x plus 4 over x squared, 1 minus 2 over x plus 1 over x squared. And again here, in this case, because this is a rational function, we should approach the same value on either side, but we just want to double check and make sure here. So 5 over x, as x approaches negative infinity, it's still going to approach 0. Plus 4 over x squared, numerator is a constant, denominator has a positive power of x, so that goes to 0. In my denominator, 1 is a constant, so that stays where it is. Minus 2 over x, that's going to approach 0. Plus 1 over x squared, that's going to approach 0, so I have 0 over 1, which is once again 0 here. So I've determined the end behavior. The other piece of this says if there are any horizontal asymptotes, find them. And if you have the end behavior, the horizontal asymptotes should follow naturally. The horizontal asymptotes are just going to appear as any finite values you might get back for your end behavior. So if I wanted to talk about my horizontal asymptotes over here, I would say I have a horizontal asymptote at y equals 0. So let's take a look at another one here. G of x. This time I have 16x cubed minus 8x plus 9 divided by 4x cubed minus x squared plus 3. Again, if I look at this, so let's start with the right-hand end behavior, limit as x approaches positive infinity. I've got 16x cubed minus 8x plus 9 divided by 4x cubed minus x squared plus 3. So this is equal to, oops, let's not get too carried away here. I'm going to multiply this by, again, I'm going to determine the highest power of the denominator. And in this case, it's x cubed. So I'm going to multiply both my numerator and my denominator by 1 over x cubed. And again, I'm going to take that, I'm going to distribute that to each term in my numerator and each term in my denominator. So limit as x approaches infinity here. Let's see, I should have 16x cubed over x cubed minus 8x over x cubed plus 9 over x cubed. Divided by, in my denominator, I have 4x cubed over x cubed minus x squared over x cubed plus 3 over x cubed. And just like last time, okay, we've got some powers of x here and here. We can do some simplifying. So let's go ahead and do that at this point. So limit as x approaches positive infinity. Let's see, I should have 16 minus 8 over x squared plus 9 over x cubed divided by, in my denominator here, I'll have 4 minus 1 over x plus 3 over x cubed here. So now I can just look at the limit of each one of these. So let's take them one by one. First of all, 16, that's just a constant, so that's just going to approach 16. Next up, I have minus 8 over x squared. Well, my numerator is a constant, denominator is a positive power of x. Well, that's going to go to 0. Next term, 9 over x cubed, same thing. Anytime you're left with a constant in your numerator and a positive power of x in your denominator, and x is approaching positive or negative infinity, it's a safe bet that that value is going to approach 0. And that's kind of the whole point of this technique, is you're really just forcing most of it to go to 0 so that we can focus on the important parts of this rational function. In my denominator, I've got 4, that's a constant, so that will approach 4. Minus 1 over x, that should approach 0. And 3 over x cubed, that should approach 0. I have 16 over 4, which is 4. So here is my right-hand end behavior. So let's do the left hand really quickly, just so that we have all of it. And again, I'm out of room, so I'm going to go ahead and erase this. Let's do it in a different color here. So here, limit as x approaches negative infinity. Again, I'll use this quote-unquote simplified version right here, this version that's a lot easier for us to take the limit of. So 16 minus 8 over x squared plus 9 over x cubed divided by, in my denominator, I've got 4 minus 1 over x plus 3 over x cubed. And regardless of x is approaching positive or negative infinity, these are mostly either constants or simple rational functions, in which case they should approach the same value. So 16 is a constant, that'll still approach 16. 8 over x squared, well, x is approaching negative infinity here, so that's still going to approach 0, just from the other side. Actually, no, since this has a positive power, it would approach from the same side. 9 over x cubed, though, that'll also approach 0. In my denominator here, I've got 4, that's a constant, so that'll stay where it is. Minus 1 over x, that'll approach 0. 3 over x cubed, that approaches 0. 16 over 4, once again, I have 4 this time. And again, just the last part of this, if I want to talk about the horizontal asymptotes, I've got 4 for both, so I have a horizontal asymptote at y equals 4 then. Alright, let's take a look at one more here. So this time I have h of x equals 6x cubed plus 4x minus 1 all over 8x plus 2. So let's get my blue out. So limit as x approaches infinity here, I'll have 6x cubed plus 4x minus 1 divided by 8x plus 2. So once again, I'm going to look at the highest power of x in your denominator. Here it's really x to the first power, so I'm going to multiply both my numerator and my denominator by 1 over x, and take that and distribute that. And if you want to kind of simplify this as you go, that's totally fine here. Limit x approaches infinity. So 6x cubed over x, I know that's going to simplify to be 6x squared. Plus 4x over x, I know that's going to be plus 4. 1 over x, that'll be 1 over x. In my denominator then, let's see, 8x over x, that should be 8 plus 2 over x. And then we can see where this leads us. So in my numerator here, let's see, 6x squared, this guy. So this is something a little bit different happening here. I have 6x squared here as x approaches infinity. That will approach a positive infinity. So there's something a little bit different happening here. Plus 4 is a constant, that's going to go to just 4. Minus 1 over x, that should approach 0. In my denominator, 8 is a constant, so that approaches 8, plus 2 over x, that should approach 0. So essentially I've got infinity plus 4 minus 0, but infinity plus or minus any finite number is always going to be infinity, so that's fine. Divided by 8, well, infinity divided by any positive finite number is still infinity. So here's one of my end behaviors, kind of the right-hand end behavior here, is positive infinity. And then again, I can do the left-hand end behavior fairly quickly based off of this. So here, limit as x approaches negative infinity here. Once again, I'm going to use this, this form that's a lot easier for us to work with. So 6x squared plus 4 minus 1 over x all over 8 plus 2 over x. So once again, this time we will have to pay attention to the power here. So here I have 6x squared, x is approaching negative infinity. In this case, since we have an even power of x, that will still approach positive infinity, but that is something that you're going to want to be aware of here. It is something that you're going to want to keep an eye out for. If this had been 6x cubed instead, right, if this was 6x cubed, then I would have a negative infinity. So just be very careful with that. 4 is a constant, that should approach 4, 1 over x, that goes to 0, over 8 plus 0. In this case, I'll have infinity over 8 once again. So once again, my left-hand end behavior, positive infinity. It is possible for us to have different end behaviors on both the left and the right-hand side, which is why it's so important that we check both of them. For the last part of this problem, then, we need to determine the horizontal asymptotes, if we have any. Well, one of my end behaviors as x approached positive infinity, while y value also approached positive infinity. And here, as x approaches negative infinity, y will approach positive infinity. So on either side, I'm not approaching a finite value. And what that means for me in the end, then, is that there are no horizontal asymptotes. So if you don't end up with a finite value for your end behavior on either the left or the right hand side, that means that your function has no horizontal asymptotes.